Hey there, Year 5. Welcome to today's explainer, the long jump mystery, Demystifying Decimals. We are about to crack a real-world sports mystery and uncover some pretty incredible numbers hiding right in plain sight. So get ready to activate those mathematical brains of yours, because by the end of our time together, you'll be looking at the world in a totally different way.
Okay, let's dive right into this. I want you to picture the scene. You're in a massive stadium, the crowd is absolutely roaring, and you're watching a track and field competition. An athlete sprints down the runway, hits the board, and just flies through the air. The athlete here has jumped way past the 7-meter mark, but if you track where his feet land, he hasn't quite reached the 8-meter line either. He's kind of floating somewhere right in between.
So, here is our big question. How far could that jump actually be? Take a second to really think about that. If it's more than 7, but less than 8, our regular, everyday whole numbers just aren't going to cut it to solve this measurement problem, are they? We can't just call it 7 meters, and we definitely can't call it 8 meters. We need a way to describe that exact space between the whole numbers. And honestly, that specific problem is exactly why decimals were invented. To solve this mystery, we need to make sure our detective toolkits are packed with the right vocabulary. Here are our essential maths words for today's investigation: meter, tenths, decimal, whole, ones, and represent. These are all super important, but the absolute most crucial tools for today are tenths and decimal. Lock those two words into your brain right now because they're going to unlock everything we do next.
All right, moving on to our next section, zooming in on tenths.
And this brilliantly illustrates what happens when we pull out our mathematical magnifying glass. We start at the whole number 0, and we end at the whole number 1. But look at what happens when we zoom in on that space. It's perfectly sliced into 10 equal parts. We aren't just leaping from 0 to 1 anymore, we're taking 10 tiny equal steps to get there.
Let's formally define what we're looking at here. Tenths. Each part is 1/10 of the whole. Think about that relationship for just a second. If you take a single whole 1 and snap it into 10 identical smaller pieces, you get tenths. This means that tenths are literally 10 times as small as ones. It's a really brilliant way of breaking down the world into much more precise pieces. So, the crucial point is how we actually write this stuff down. You probably already know how to write 1/10 as a fraction, a 1 over a 10. But check this out. We can also write it as the decimal 0.1. The fraction 1/10 and the decimal 0.1 mean the exact same thing. They're basically mathematical twins, just wearing slightly different outfits.
Which brings us to section 3, the place value chart.
Now, what's really interesting about this place value breakdown for 2.6 is that you can think of this chart as our ultimate decimal rulebook. It breaks a number completely apart and tells every single digit exactly where it belongs. Look at how 2.6 is built. We have our tens, our ones, that super important decimal point, and then our new best friend, the tenths column. We have a 2 sitting perfectly in the ones column, and a 6 right there in the tenths column. So let me ask you a quick question to test those detective skills. How many ones are there in the number 2.6? I'll give you a second. number 2.6. I'll give you a second. Did you spot the 2 in the ones column? Yep, exactly right. There are 2 whole ones.
When we chat about this number out loud, we read it as 2.6. And let's focus on that second part. It has 6/10 sitting right after the decimal point. If we wanted to write that piece all by itself, without the whole numbers, we'd write 6/10 as the decimal, 0.6. Now, I really want to challenge you, Year 5. Can you explain why 2.6 is actually made up of 26/10? Try to visualize it in your head for a second. If one whole block gives you 10/10, then 2 whole blocks would be 20/10, right? Combine those 20/10 with the 6 extra tiny tenths we have after the decimal, and boom, you've got 26/10 in total. It's totally amazing how numbers can stretch and combine like that. All right, next section, naming decimal numbers. Let's do some reading practice together. Same out loud with me wherever you're sitting. First up, we have 4.7. Then we flip it around to get 7.4. Next is 0.4. Then our double digits, 4.4. And look at these larger ones down at the bottom. Even though they have tens in them, the rule stays exactly the same. We have 74.9 and finally 94.7. See how place value works seamlessly no matter how big or small the number is? Did you happen to notice the third number on our practice list, the 0.4? Our source text actually gives us a really specific rule for this. We use the word 0 to help us say numbers that include the digit 0 in the ones position. That 0 is so important. It's holding the place of the whole numbers, letting us know clearly that we only have fractions of a whole, specifically 4/10. Without that 0, the decimal point could easily just get lost. And now our final major section, showing decimals many ways. Let's move on and see how this builds on everything we've learned so far. This is a bubble map created by a student named Gus. Gus was given the task of representing the decimal 3.5 in as many different ways as possible. Just look at all these brilliant ideas he came up with. He used a number line, he wrote it in words as 3.5, he drew counters, he filled out a place value chart, the whole shebang. But let's act as math detectives for a second and critique Gus's map. He did an awesome job on most of it. His number line position, right halfway between 3 and 4, totally correct. Writing it as 35/10, correct again, just like our 26/10 example earlier. Place value chart, spot on. But wait, look really closely at that fraction he wrote at the bottom. He wrote 3 and 5 over 100. Hold up, we're working with tenths, not hundredths. That bottom number absolutely needs to be a 10. Great spotting, detectives. And that brings us to your mission. Now represent the number 2.9 in different ways. Seriously, I want you to grab a piece of paper and a pencil right now. What apparatus or sketches can you make? Can you draw a perfect place value chart, a number line? Can you actually beat Gus's bubble map? What is the absolute most unusual way you can represent 2.9? Thank you so much for joining me on this explainer, Year 5. Keep questioning, keep investigating, and I'll catch you next time.